Welcome to this module, and in this module we will see some more characteristics of an operational amplifier. Until now we have seen few characteristics of an operational amplifier, including the block diagram of an op-amp, and we have also solved one problem related to the input bias current and input offset current, right. So, here let us see few more characteristics of operational amplifier, and that will be the end of this particular module, and then we will continue the circuits of op amps in the next lecture. Okay. So, if you come to the screen, what we see here is realistic simplifying assumptions, right. There are few assumptions that is realistic, and we will assume something. The first one is 0 input current. First one is 0 input current. So, what is it? The current drawn, this is what we are assuming, that is why it is realistic and simplifying assumption. The first assumption is the current drawn by either of the input terminals, inverting or non-inverting, is 0. This is our first assumption, that the current drawn by either of the input terminals. So, when we say either of input terminals means we have two terminals, inverting terminal, non-inverting terminal, and we have output terminal. What we are assuming is that the current drawn by inverting or non-inverting terminal is 0. Okay. In reality, the current drawn by the input terminal is very small, that we have seen, right. By understanding input bias current, input offset current, we saw that there is a very small current that flows in the inverting and non-inverting terminal, which is order of microamps to nanoamps, right. Hence, the assumption of 0 input current is realistic. Hence, the assumption of 0 input current is realistic, right. Second, and the most important concept in op amp is the virtual ground. What is virtual? Virtual means not real. So, what is it? This means that the difference in input voltage Vd between the non-inverting and inverting input terminal is essentially 0. This is obvious because even if input voltage is a few volts, due to large open loop gain, the difference of voltage Vd at the input terminal is almost 0, correct. So, the differential voltage Vd will be what? Vd will be V at non-inverting minus V at inverting, right. This is a differential voltage. We assume that the differential voltage is essentially 0. If this is essentially the 0, then this is obvious because the input voltage, even if it is few volts, due to large op amp, the difference of voltage Vd will always be 0. Let us see an example. Okay. So, if our output voltage is 10 volts and AOL, that is open loop gain, is 10⁴, then what we can write? VO equals to Vd into AOL, right. VO is our output voltage, Vd is the difference voltage. So, from here Vd will be VO upon AOL, or Vd will be very small, which is 1 millivolt. Now, hence Vd is very small as AOL is infinite. See, for 10⁴ you can get Vd of 1 millivolt, but if I increase to 10⁵, if I increase to 10⁶, if I go on increasing to 10 to infinite, then what will happen? Or in fact 10 to infinite. What is this values? These are the values of open loop gain. If I keep on increasing the open loop gain, my Vd will come near to 0. My Vd will come approximately equal to 0, right. Vd will be approximately equal to 0. So, the point that we are making here is that the difference voltage Vd is 0 and realistic assumed to be 0 for analyzing the circuits, right. So, if I have this particular equation, which is very easy to understand, that the output voltage is nothing but difference of the input voltage Vd into open loop gain AOL, right. So, if I want to have Vd, then Vd is nothing but VO divided by AOL. Now, in this particular case our Vd, our output voltage is given, our open loop gain is given, right. That means we can have Vd equals to output voltage is 10 volts divided by open loop gain is 10 raised to 4, right, which gives us answer of 1 millivolts, which gives an answer of 1 millivolts, right. Now Vd is very small, right, Vd is very small, and as AOL tends to infinite, as AOL goes towards infinity, right, the difference voltage Vd will become 0, correct, and the realistically assume 0 for analyzing the circuits. So, that means that this is also a realistic simplifying assumption saying about the virtual ground. Let us further see, right. So, if I put infinite as AOL value, if I put infinite as AOL value, my Vd will becomes 0, right. Therefore, if Vd is 0, if Vd is what? Vd is V1 minus V2, right, or in another way I can also write Vd is nothing but my voltage at non-inverting terminal minus voltage at inverting terminal. If I have Vd equals to 0, that means my voltage at inverting terminal should be equal to voltage at non-inverting terminal, right. Right, this much is easy. So, if that is the case, what we can say that, thus we can say that under the linear range of operation there is a virtual short circuit between two input terminals, in the sense that their voltages are same and no current flows from input terminals to the ground, right. So, if I draw a circuit, and if I have ground here, then this terminal minus and plus, let us say this is V minus, this is V plus, then this is at virtual ground because this is ground, this is a virtual ground because this is ground, right. That is what we have understood until now, correct, because if I have, if my gain is different, then I will have different value of input voltage, but difference voltage Vd, but if my gain is infinite, my Vd will be 0, and if Vd is 0, that means my non-inverting terminal is same at inverting terminal. If inverting terminal is grounded, non-inverting is also grounded, that means it looks like we are shorting the, we are virtually shorting the two ends of the op amp, two input terminals of the op amp, right. So, this circuit what you can see here, right, sorry, inverting, non-inverting, this is RF, this is R1, this is current, ground. Now, what we are saying is this particular terminal will be similar to this terminal because of the concept of virtual ground, right. This is what circuit is, this is what the circuit is. Okay. So, there is a virtual short. Now, if the non-inverting terminal is grounded, by the concept of virtual short, inverting terminal also is at ground potential, though there is no physical connection between inverting and the ground. You see, is there any physical connection like this, No, right? There is no physical connection which or a wire that connects the inverting and non-inverting terminal, correct. So, now if the non-inverting terminal is grounded, if this terminal is grounded, then by the concept of virtual short, the inverting terminal is also ground potential, though there is no physical connection between the inverting and the ground. As there is no physical connection between inverting terminal and ground, this is also called virtual ground. This is also called virtual ground, right. Thus, we can realistically assume that voltage at the non-inverting terminal of the op amp is equal to the voltage at the inverting terminal. Why? Because my Vd would be 0, because my V inverting and V non-inverting and V inverting voltages are same. Suppose this is x, this is also x, and Vd is nothing but V plus minus V minus x minus x, same value. So, this will be 0. So, my answer is 0. If this is a 0, that means I am assuming that V plus and V minus are connected. If V plus is grounded, then V minus is also called virtual ground. This is the concept of virtual ground. Alright. That means that we can realistically assume that the voltage at the non-inverting terminal of the operation amplifier is equal to the inverting terminal, alright. So, this is what is your virtual ground. Now, I hope that you guys can understand, right, what we mean by virtual ground, correct. Now, we know what we mean by virtual ground. So, let us see some other characteristics. Let us see other characteristics of operational amplifier. Alright, let us see some more characteristics of an operational amplifier, starting with differential mode gain. So, what is differential mode gain? Differential mode gain is given by AD. Gain is A, differential mode, that is why D. So, we have a symbol AD for differential mode gain. What is it? It is a factor by which the difference between two input signal is amplified, right. It is a factor by which the difference between two input signal is amplified by the op amp, alright. So, if my VO equals to AD into V1 minus V2, AD is gain with which differential amplifier amplifies the difference between two input signals, and it is also called differential gain. That is, if I have VO, I am writing the same equation, AD into V1 minus V2, right. In this case, if my V1 is 2 volts, V2 is 1 volt, right, then my VO would be nothing but AD into 2 minus 1, that is AD into 1, and what is my AD? Whatever my gain of AD would be there, my difference voltage would be amplified by that particular gain, and that is why AD is called differential mode gain. Correct, easy. So, now we know what do you mean by differential mode gain, right. Now, we know what you mean by differential mode gain. Concepts are really easy. If you really think, what we are looking at is we are just looking at some equations which are so simple to understand, right. So, when you talk about differential mode gain, you can easily see it is a difference of voltage, and we are amplifying the difference, and that is why it is a differential mode gain, right. So, now let us see the another concept, which is the common mode gain. So, when we see common mode gain, we will see a little bit different than compared to differential mode gain. So, if you see common mode gain on the slide, what we see, that it is a factor by which the common mode input voltage is amplified by the op amp. It is a factor by which the common mode, this word very important, input voltage, common mode input voltage is amplified by the operational amplifier. So, what does it mean? If we apply two input voltages which are all in equal respects to the differential amplifier, which are equal in all respects, then V1 equals to V2, correct, then V1 equals to V2. So, that will give us, we have this one, VO equals to AD into V1 minus V2. If I say I am applying V1 equals to V2, that is my voltages are same at the input of terminal, that implies that my VO is nothing but AD into 0, or VO is nothing but 0, because V1 is equal to V2, correct. Because V1 equals to V2, my output voltage will be 0. This is what we are saying, that if we apply two input voltages which are equal in all respects to the differential amplifier, then my output voltage must be 0. But the output voltage of the practical differential amplifier not only depends on the difference voltage, but also depends on the average common mode level of two inputs, you see. So, it does not only depends on differential voltage, but also depends on the average common mode level of input. Such an average low level of 2 input signal is called common mode signal, denoted by Vc, denoted by Vc. Okay. So, if I want to know the common mode signal, this is nothing but average of V1 plus V2 by 2, V1 plus V2 by 2. Okay. Practically, the differential amplifier produces the output voltage proportional to such common mode signal. Also, the gain with which it amplifies the common mode signal to produce the output is called the common mode gain of the differential amplifier, denoted by ACM, denoted by ACM. So, what does it mean? That when we take a amplifier, right, and we insert the amplifier in this circuit, then what we see is that the output voltage is proportional to such common mode signal. So, it is also proportional to Vc, okay, and the gain with which it amplifies this Vc is called my common mode gain, is called common mode gain, right. Either I say ACM, I can also say AC, okay, I can also say AC, common mode gain, right. This is common mode voltage, Vc or Vcm, Vc or Vcm, common mode voltage, alright. So, now let us read once again this sentence and we will understand what is that mean. Practically, the differential amplifier produces the output voltage proportional to such common mode signal. The gain with which it amplifies the common mode signal to produce the output is called the common mode gain, ACM. So, now my VO will not only depends on AD, V1 minus V2 is what? VD, plus it will also depend on ACM and VCM. Now, it will depend on the common mode gain and the common mode voltage. So, my new formula for output voltage will be AdVd plus ACM VCM, AdVd plus ACM VCM. Okay. So, in this particular case, I will use this common mode signal, I will use the common mode gain, differential gain to understand a very important property which is called common mode rejection ratio, common mode rejection ratio, a very important term for an operational amplifier. Okay. The ability with ability of a differential amplifier, not with, ability of a differential amplifier to reject common mode signal is expressed by a ratio called common mode rejection ratio, right, because we do not require common mode signal, we only require the differential signals AdVd, this is what we require. See, in equation, in the equation what we have written, AdVd plus ACM VCM, right, VO equals to this one. But in reality common mode signals we do not want common mode signals, we only want the differential signals, alright. So, if I know the ratio, if I know the that a differential amplifier can reject the common mode signal, by a ratio called CMRR, common mode rejection ratio. It is given by mode of AD by ACM, differential gain divided by common mode gain. So, ideally common mode voltage is 0, ideally common mode voltage should not be there, right. So, ideally ACM should be 0. If ACM is 0, my CMRR would be nothing but infinite, CMRR would be infinite, that is what is done, right. Ideally common mode voltage gain is 0, hence the ideal value of CMRR is infinite, right. But for practical differential amplifier, AD is large, ACM is small, this CM should be in subscript, D should be in subscript, right. AD should be large, ACM should be small, right, hence the value of CMRR is also very large. So, practically we cannot have ACM equal to 0, practically this is not possible, right. But ACM can be close to 0, then if ACM is close to 0, let us say 0.001, then what will happen, my CMRR would be very high, would be very high, but not infinite, but not infinite. It will be very high, but not infinite. Okay. So, CMRR is also many times expressed in decibels. It is expressed in decibels. Okay. And CMRR is nothing but 20 log AD by ACM. CMRR is 20 log AD by ACM. This is a value when we have to express in decibel. So, now if VO equals to ADVD plus ACM VCM, if I keep common ADVD, then finally I will get equation which is similar to this, So, this equation explains that a CMRR is practically very large, though both VC and VD components are present. You can see VD and VC are present, still the CMRR is very large. The output is mostly proportional to the different signal only, and common mode component is greatly rejected. Now, to understand whatever we have told about CMRR, we have to perform the we have to solve some problem. Then we will understand how CMRR is important. Okay. So, let us perform one exercise. And that exercise is, we have to determine the output voltage. Of a differential amplifier. So, what is that? We determine the output voltage of differential amplifier. So, VO is nothing but AD VD plus ACM into VCM, right. We know this formula. Now, we are given input voltages. This is input voltage 1, input voltage 2. So, we are given V1 300 microvolts, we are given V2 240 microvolts. The differential gain of the amplifier is 5000. So, we know that AD is also given, AD is given 5000. Now, and the value of CMRR. So, for two values we have to calculate. First value is given as CMRR equals to 100. Second value is given as CMRR equal to 10 raised to 5, right. So, for the first one CMRR equals to 100, VD is what? VD is nothing but V1 minus V2. So, we will substitute V1 V2. So, we get VD which is 60 microvolts. What is VC? VC is V1 plus V2 by 2, we substitute 300 plus 200 by 2, we get 270 microvolts, right. What is CMRR? CMRR is AD by ACM, right. CMRR is AD by ACM. So, we have CMRR for 100, AD we have 5000, right. AD we have here 5000 by ACM. From here what we will get? We will get ACM equals to 50. From here what we get? ACM equals to 50. So, now what we know? We know VD, we know VCM, we know ACM, right. So, let us substitute its values in VO. So, VO will be AD VD plus ACM VC. So, what is AD? AD is 5000 here, given here, right, 5000. Then 60 is what? My VD, right, plus what is my ACM? 50. What is my VC? 270, right. When I solve this, what I get? 313.5 millivolts, okay. This was easy. Now, let us do the same calculation with CMRR equals to 10 raised to 5. When CMRR is equal to 10 raised to 5, what will be my answer? So, for CMRR equal to 10 raised to 5, ACM equals to, you know that is equation, right. CMRR equals to AD by ACM. So, ACM would be nothing but 0.05, right. If I substitute this value again in this equation, rest of the things remain same, right. Only my CMRR would is 10 raised to 5. So, my ACM would change. In this case, when I substitute the value, same value, this is new value 0.05, this is same value like previous example. So, what we have? Our value is 300.0135 millivolts. Here what was the value? 313.5 millivolts. Here we have 300.0135 millivolts. Now if I see, ideally ACM must be 0, right, and output should be equal to AD/VD only. So if I just say ideally my ACM VCM should not be there, correct, and my VO should be nothing but just AD into VD. This is ideal situation. So what is AD? AD, let us see, AD, where is AD? 5000 into VD. What is VD? VD is 60, right. What is 60? 60 microvolts, right. So my answer would be 300 millivolts. 300 millivolts. This is the ideal situation. This is the ideal situation when I have ACM VCM is not there, because common mode signal should be 0, right. This is the ideal situation. My output should be 300 millivolts. Now you see which value we obtained, which output voltage is close to 300 millivolts, whether it was a CMRR equals to 100 or it was CMRR equals to 10 raised to 5, whether it was CMRR equal to 100 or CMRR equal to 10 raised to 5. We will see that when you use CMRR equal to 100, my output voltage that we got was 313.5, my output voltage should be close to 300 millivolts, but when I use CMRR equal to 10 raised to 5, when I use CMRR equal to 10 raised to 5, my output was 300.0135, which is close to 300 millivolts. 300.0135 is close to 300 millivolts. That means what I see is, if I keep on increasing CMRR, my output is close to my ideal value. My output is close to my ideal value. Okay guys, so for this particular module we will stop here. Now you know how to use the CMRR and what are the common mode gain, what are the differential gain, what are common mode voltage, what are differential mode voltage. We have seen an example. Now if somebody asks you in a exam or in a viva that if what should be the CMRR, it should be high, it should be low, it should be then you can answer very easily. The CMRR is a common mode rejection ratio and it is given by differential voltage by common mode voltage, common mode gain, differential gain by common mode gain, and CMRR is expected to be extremely high because we do not require any common mode signal, right. You can also say that as your common mode signal is low, my CMRR would be extremely high. If my CMRR is high, my output voltage will be close to my realistic or ideal value, which is VO equals to AD/VD, because in reality VO equals to AD/VD plus ACM VCM, but ideally my VO would be AD into VD. So if I do not want to consider ACM VCM in practical situation, I cannot just ignore ACM VCM. So in that case, if my CMRR is extremely high, my output voltage would be close to my ideal voltage, right, and thus the importance of CMRR comes into picture, right. So now you guys know how to use CMRR, you guys know how to use the this is a parameter, this is one of the parameter of a differential amplifier or a realistic parameter of operation amplifier. You have also seen what is virtual short, very important parameter, virtual short, right. Now in the next module we will see few more parameters of the operation amplifier. Till then you just read once again whatever I have taught, and I will see you in the next class. Bye.